Welcome back, mathletes, to another episode of Math with Dr. Math, and we're here today to talk about compound inequalities. All right, so this is a nice topic because it's a topic that people get confused on all the time, and I'm here to unconfuse you, all right, to help you out. So check it out. When we're looking at compound inequalities here, what we're looking at is two inequalities, right? And they're going to be joined together either by an and or an or statement. So you're going to see two inequalities and it's going to say and or. And here's some examples of, how they might look. So here we have x is greater than -2 and x is less than 5. And we're going to be graphing these. We're going to see what that final solution set looks like. We'll be talking about all that good stuff. And here's an example of what an or statement would look like. So let's get our hands dirty and let's dive in. But what I want to do is I want to break these up individually to show you what to look for. So like always, before we begin, we put a lot of time into this. So do us a favor, pay us, but with a like, all right? And go ahead and subscribe and let's get started here. So let's start with and compound inequalities. So what we're going to do, just like we stated, we're going to have two inequalities here. So here you have x is greater than -3. So that's all the numbers that are greater than -3. But notice we have an open circle here because you are not including that -3. Some books use an open circle. Other books use this open parentheses here. Right? They mean the same thing. It's just a different notation depending on who the author is. The second inequality here says that x is less than 5. So you have an open circle here because you're not including 5. If you were, it would be a solid circle, and it's all the numbers to the left, all the numbers that are less than 5. So when we talk about an and statement, what we're looking at is what do these two graphs have in common? So we're looking for some common ground. And this solution set that you see here, notice, these are all the numbers that both of these sets have in common. And the endpoints, notice they're open circles because this graph up here did not include -3. So that's why it wasn't included in both graphs. And this bottom graph right here was not including the 5. So that's why I had an open circle. So sometimes that's a tricky subject or, tricky idea to work with. So again, the only way for these to be closed circles would be if those points were actually included. All right. So let's go ahead and let's look at these and statements. So again, and statements, they state what do these graphs have in common. All right, so for our first example, we have these two inequalities. So what you're going to do is you're going to solve each one of these inequalities one by one. So let's go ahead and solve this one. And what's nice is the solving part is going to be quite easy because that's what you're familiar with. So we're left with x is less than 8. X is less than 8. So I'm going to go to 8. We're not including it because you do not have a line underneath here, so it's an open circle, and x is less than. So remember, less than is all the numbers to the left. Some books write it just like that. Others will actually shade all this. It means the same thing, just different notation. All right, so let's go ahead and do the same thing with this other inequality here. So I'm going to subtract 4 from both sides. So we treat it just like an equation. And you get 2x is less than 10. Divide by 2, divide by 2. So you get x is less than 5. So on this graph you have 5. Again, you have an open circle because you're not including that 5. And it's everything to the left, to the left, to the left. All right, so now we look at both of these graphs and you ask yourself, what numbers are included in both graphs? So we could see that all the numbers from 5 all the way to -infinity are included. So for our final solution, we start at 5 And it's an open circle because notice it wasn't included in this graph. And you shade everything to the left. So our final solution set is x represents all the numbers that are less than 5. Right? So that's how we would write that inequality, but this is how it would actually look on our number line. Some of you may be familiar with interval notation. So you can use interval notation, and remember what that means is how far to the left is this graph going? Well, it's going to negative infinity. How far to the right is this graph going? Well, it stops at 5. Does it include 5? Well, no. So that's why we have an open parentheses to tell the audience 5 is not included. All right, so there's our first example. Are we good? Any questions? Perfect, let's move on. All right, so now let's talk about the OR statement. So the nice thing about OR inequalities is in the problem, it'll say the word OR, right? It'll give you two inequalities and it'll say OR. So what we're gonna look at here is x is less than -3. So this graph right here represents, the left side represents x is less than -3, or x is greater than 5. So x is greater than 5, we start at 5 and all the numbers to the right, which are greater than 5. So for our solution set, our final answer, when we look at OR, what we're looking at is the total collection in numbers from both graphs. So in this case, we don't care about what they have in common. We want everything. We're bringing everybody to the party, okay? So here we go. So let's do an example. So we're gonna solve this inequality. So just like we did before, we're gonna isolate the x value. So let's go ahead and let's isolate the x value. So we're gonna add 3 and add 3. So you get 2x is less than 10. All right, continue the march. Divide both sides by 2, divide both sides by 2, and here we have x is less than 5. All right, so x is less than 5. Here's 5, and we're going to the left. Bam. All right, so next one, we're gonna go ahead and solve for x. So let's subtract 35 from both sides. Subtract 35, and we get -4x is less than or equal to 3 minus 35, which gives us -32. So we're going to go ahead and divide by -4 because we're trying to isolate that x. And notice, make a note of this, when you divide by a negative, you have to change that inequality. So now instead of saying less than or equal to, now it's more than or equal to. So make a note, when you divide by a negative, this inequality changes its sign. Same thing is true if you multiply, all right? So jot that down, and we get 8. So here we have our 8, and notice it's included. It has that line underneath. So because it's included, check out what I'm doing. I have a solid circle. Again, some of your books may use the closed bracket that looks like that. It means the same thing, just different notation. And we're gonna shade everything to the right. All right, so for our final answer, our final solution, what we say is we include everything that you see. So you have x is everything that's less than 5, or x can also be anything that's 8 or greater. So this is what the graph of that solution looks like. So it looks like x is less than 5, or x is greater than or equal to 8. Again, if you want to use interval notation, this is what it looks like. We start from left to right. So from the left, you could see this graph right here is going all the way to -infinity. So we go from -infinity, and it stops once it gets to 5. We have an open circle because you don't include 5. And whenever you have an OR and you're using this interval notation, this is our OR symbol. So let me write that down. This is our OR symbol. our union. All right, it's called union. For and, we have the intersection. All right. And so here we're doing an or statement. So we start back up at 8, but notice we need a closed bracket there because you are including the 8 and all the way to infinity. So again, this graph, let me show you, starts at 8, you include it with your square brackets, and it goes all the way to infinity and beyond. All right, so there's our example of an or statement. Feel good? Let's do another one more. And before we start, hit that like button. All right, help us out. All right, mathletes, here we go. Let's close up shop here. Let's go ahead and add 5. So you get 3x is less than or equal to 18. Divide both sides by 3. Do we have to change the inequality here? Good. No, because you're not dividing by a negative. So only when you divide by a negative. The other one, let's go ahead and solve it. -2 minus 2. So you get 5x is greater than -5. Let's go ahead and divide by 5. Divide by 5. So x is greater than -1. Some people get confused because you see a negative there. It's only when you divide by a negative, that's when you change that sign. So here we're good. Let me go ahead and put my or statement. So here we go. I'll do this first one in black. So x is greater than, x is less than or equal to 6. So I closed in my circle there. This other one I'll do in red. X is greater than -1. Open circle. And so I'm going to ask you, what numbers were shaded? What numbers were included in this? Well, you could see that every single number on this number line is included. So in this case, because we have an or statement, everything's shaded, right? There's no number that's excluded here. So our answer here, I could shade everything, right? So our final answer is all real numbers. So this is our interval notation. Or if you want to use set builder notation, if you're interested in set builder notation, comment down below. We can make a video about it. And x could represent any real number. That's our fancy math way right there of telling our audience x could be any real number. Boom. All right, folks, so now you know about compound inequalities, you know about or statements and statements. Hopefully this was helpful. Give us a subscribe, and we'll see you mathletes in that next video. Peace.